Hey, welcome to another video. In this video, we're going to continue talking about how to solve differential equations with usually separation of variables or our linear differential equation techniques, but involving some substitutions. So we're gonna do that with something that we like to call obvious substitutions. And the first thing I want to say is that obvious does not always really mean obvious. So kind of like in a textbook, you read through it and you say the rest of the proof is obvious. You go, that's not obvious, to me at least. So I'm going to show you what to look for when we deal with these other substitutions. So this class of equations, differential equations, might not perfectly fit homogeneous model or Bernoulli or a embedded derivative, but maybe it's an obvious substitution. So I'm going to show you what that means. I'm going to show you 3 examples on how to approach these, and hopefully that'll make sense to you. So if you remember our goal with substitutions, it's put it in a proper form, use some sort of a substitution to change it into either a separable equation or a linear equation, and then we can use the techniques we've already learned, or a basic integral. So let's look at these obvious substitutions, find out what they mean, and then do a few examples. So sometimes we can get some substitutions that are obvious. Here's what you're looking for. Here's what obvious means. Obvious means that what you're going to substitute is typically a composition. So look in your differential equation for a composition. What a composition means is you have one function inside of another form of a function. And we're going to look at that right there in just a bit. So you're looking for a composition. Like in this case, well, hey, you have 4x plus y inside this other function of something squared. That's a composition of functions. We're going to identify that as some v. I want to tell you right now that this technique is very, very, very similar to the homogeneous equations that we just learned how to do. So in that, we made a certain type of substitution. We did y over x. We said, okay, that's going to be v every single time. And then if we do that, we'll solve for y every single time. Then we'll take a derivative every single time, and it'll be the same every single time. This is very similar. Only this time, the derivative isn't always the same. What you're substituting isn't always the same. What you're substituting is just a composition. Just like homogeneous equations. That was a composition. That was y over x. And we changed that into v. That would have been a composition of something inside of another function. So we chose a basic composition. Here we're doing the same thing. It's just we're not always choosing y over x. We're choosing some composition and hoping that it works. So we're going to be looking for a composition, something that you can solve for y. Why is that important? Well, if we choose a composition and say, hey, let's find a composition, let's call it v. Okay, if we solve that for y, no problem. Then when we take a derivative, we can make this, same idea as a homogeneous, this double substitution idea. Call your composition v. Then if you take a derivative after solving for y, you have something you can replace dy dx with, because you can't have that y anymore. So our main idea, very similar to homogeneous, you're looking for a composition, we're solving for y. We're going to replace all of the y's from the composition and the dy dx by the derivative. So just like homogeneous, you can't have any y's left over. Let's see how that works. We'll run through a few of them and then we'll call it good. So let's take a look at this first order differential equation. We're looking at it, we're going, wow, that isn't separation of variables. I really don't want to distribute anything. Doesn't look homogeneous, or if it is, it'd take a long time to get there. It doesn't look linear. I've got a power 2, so what in the world could I do here? This is one of those cases when we have a composition of functions that wraps up all of our y's. That's big. All of the y's inside that composition. And it's right here. So that 4x plus y, we can consider that to be a composition. So one of these obvious substitution technique, or this obvious substitution technique says, take that composition where we have a function of x and y, or just a function of y, whatever it is, inside something that's raised to a power, or that's grouped all together, or that you can call it v. Let's try that. So we're going to take our composition and say, let's call that v. I'll point out one more time that that's exactly what you did with homogeneous. It's just that the composition was always the same. The composition was always y over x. Then we solved for y. We just had y equals vx. Well, this time, if we pick a composition that we can solve for y, let's solve it for y. And the reason being is that we're about to change our differential equation. Sure, everything that involves y's here is going to be called v, and that's fine. But also we need to change that y. So when we did homogeneous, we said we got to have all the y's wrapped up in that v. We also need a way to change dy dx into dv dx, and that's exactly what this is going to do for us. So we've wrapped up our y's in a composition, no problem. We have solve for y, that's why this step is important. We got to have something to solve for y, and then we're going to take a derivative. So dy dx equals, one big note you might want to write down, or at least realize right here, this is always going to involve a chain rule, just like when we solved those homogeneous equations. What I mean by the chain rule is that right there, that's a function of x and y. So when we take this with respect to x, so we're taking a derivative of y with respect to x, well, we have the derivative of v as 1, sure, but there's a hidden function there, possibly. So we're going to have the derivative of v as 1 times dv dx, because it's an implicit derivative, just like from Calc 1. We typically don't even write the 1, we just realize that that's a chain rule, we're going to write dv dx. Minus 4, because we're taking a derivative with respect to x, we don't need to write dx dx, well that's just 1, so we don't really care about that. So we're going to make this substitution, and now we have everything lined out really like homogeneous, it's just it's not always y over x. So we're going to start changing this. We know that we called this inside function, this 4x plus y, we're going to call that part v. So we're going to get a v squared. But because we wrapped up all the y's in that substitution, we also needed to get rid of dy dx. All right, that's why we picked something we can solve for y. Because if we can solve this substitution for y, then we can take a derivative right off the bat and get dy dx equals some function in v's and x's. So we're going to make our substitution. On the right-hand side, this part is v. So we'll get v squared. On the left-hand side, we also needed to replace dy dx, and it's right here. So dy dx says, well, don't write dy dx. I don't want dy dx because I have 3 variables right now, and I can't integrate like that. I can't solve like that. So, so instead of dy dx, let's use our second part of the substitution. One substitution for the composition, another substitution for the dy dx. In this case, we had dv dx minus 4. Now, what's going to happen, just like on the homogeneous equations, is you're going to get something that's a separable equation. So we're going to try to group our variables, our v's dv on the left, our x's or constants dx on the right. So if you notice that from homogeneous, we were always getting the separable equations. We were always separating our variables and integrating. Same thing's going to happen here. So one more time all the way through, and then after this, I'm not going to really repeat that a whole bunch. I probably will because I'm Leonard, and Leonard does that. But the idea is look for a composition. If we can't make it into a homogeneous, look for a composition that you can solve for y. No problem. Solve it for y. Take a derivative and do a double substitution. All the y's have to be wrapped up in your v. It has to be wrapped up in here. Otherwise, we'd have 3 variables. That does not work. So wrap this up in a v, no problem. Take a derivative of y, that's why we have to solve for y. And then we can replace all of our y terms with some sort of v, and our dy dx with whatever the derivative of your substitution when you solve for y actually is. So let's take a look at that. If these are going to be separable, we're going to have to add the 4 and divide. Remember, separable equations are stuff that's multiplied together, not added or subtracted. So we're trying to get separable here. All right. Hey, you know what? If I move this whole piece, divide both sides by v squared plus 4, we can get 1 over v squared plus 4 dv equals 1 dx, or just dx. And now that's great. That's the form of separable equation. We've made this so we have v's dv, made this so that we have constants dx. If we integrate both sides, right side's easy. Right side's going to be x plus c. On the left-hand side, And you can do that at least two ways I know of. You can do that with a trig sub if you want to take a lot of time, or you can do it with an integration table. At this point in your math careers, there's nothing wrong with using an integration table. That's okay. I would do it for sure. When you think about this, this is a tan inverse. If that was 1, you'd get tan inverse of just v, so tan inverse of v. When that number's not 1, you start doing stuff like this. You go, okay, well, I know it's going to be tan inverse of v. That would be if this number were 1. But you can think of it like this. This is really a fraction with a square root right there. So you go, all right, tan inverse, if that was 1, that'd be square root of 1, both places. If that was 4, that'd be square root of 4, both places. So on the left-hand side, we do have a tan inverse, and that should look really, really familiar with you. We've done it several times. Even in this class, we've done that. But here, since it's not 1, usually you'd get 1 over the square root of 1. If this had been v squared plus 1, that's what you get. But now it's 1 over square root of 4. No problem. That gives us a 1/2. It gives us a tan inverse still. It gives us v over 2. And then on the right-hand side, we just have this x plus c1. Remember, we call that c sub 1 just because we might be changing it. As a matter of fact, we're going to right now. We're going to multiply both sides by 2 just to get rid of it. I don't see anything else I'm going to multiply before I start doing the tangent on both sides. So I'm going to call that, I'm going to redefine that. I'm going to redefine 2 c sub 1. Let's just call this c. It's still a constant, so no problem. Now, you'll notice something. I did this a lot on the homogeneous equations also. I solved it as much as I could for v, where it was reasonable, and then I substituted back in that substitution. We're going to do the same thing. So yeah, we call the composition v. Yeah, we solve for y because we need dy dx. We find dy dx, we make our substitution, so all of our y's become some sort of v. Our dy dx becomes some derivative that you just did from that substitution. And then you solve it with a separable equation. Okay, we got it. We got all the way down to here. Well, we're going to have to get back to y's and x's. Those v's got to go. So we use a substitution one time to get away from y's. We use it again to get back to y's. So we're going to have to do that. And we can do it anywhere you want, but I like to do it as much as possible after I solve for v, if that's reasonable to do. So let's try to solve for v. So right now I'm going to do tangent on both sides. If tan inverse of v over 2 equals 2x plus c, then v over 2 has to be tangent of 2x plus c. You know what? I can even multiply by 2. So v equals 2 tangent 2x plus c. But now we're right, I mean, obviously we've solved for v. Well, we've got to solve for y. And so let's go ahead. We use the substitution one time of 4x plus y to get away from y. Let's call it v. Now we're going to say v is 4x plus y. Are you seeing why we might want to wait to plug that in? To wait to solve for v if we can, to plug that in. I did it a lot on the homogeneous. I said, let's wait for a little bit. Let's solve it for v as much as we can that's reasonable, and then plug it in. Because if we start putting it, we could have done it right there, and right there, and right there, and right there. But that's just a lot of extra writing that we really don't need. So if we wait for a little while, sometimes it's a lot nicer to deal with, because right now, instead of writing this whole time, all we've got to do is subtract 4x, and we've solved for y explicitly. So we get this y equals 2 tangent 2x plus c minus 4x. What I want you to ask yourself right now is, are you seeing that this is really similar to the idea of homogeneous? You are making a substitution. It's actually still a composition, just like homogeneous was. You're still solving for y. You're still taking a derivative. You're still using dy dx as a substitution. And you're still using the idea of wrap up all of your y's in a v, then make a separable equation and solve it. It's pretty straightforward. This word obvious is deceiving. It does not have to have, sometimes they're not that obvious. But what you're looking for some sort of a function, like a square root, or something to a power, or a denominator, or something that you can take all of the pieces, that the inside has all of your y's, call that v. Something you can solve for y, and then this hopefully will work for you. It's something that you should try. We're going to do 2 more examples. We're going to increase the difficulty. Last one has some integration techniques that I want to show you. Just to remember, we're going to sort of refresh your memory on these things as we go. Let's try another one. So we're looking at this. We're trying to figure out if it's something that we can do directly with a basic technique, something we can substitute homogeneous, or something that we can do another substitution for. So when we take a look at that differential equation, it doesn't strike right off the bat something that's separable. X's and y's are grouped together in that factor. It doesn't look linear because if I start distributing, I'm going to have dy dx in both places. That wouldn't work that great. It doesn't look homogeneous because I don't want to start dividing by x's and y's. Maybe I could, but maybe there's an easier way. So when we have this idea of what I'm trying to do is just getting way too hard. Like homogeneous might not be the best thing to do here. Maybe it would work, I don't know, but maybe there's an easier way. And one of the obvious substitutions is look at your y's. If your y's are in some sort of another function, even if they're just a factor that contains everything, try one of these obvious substitutions. So our y is together with our x, so x plus y, sure, but it's all wrapped up in one factor. That's a composition right there. That has all of our y's in it. That's what I'm asking you to look for right now. Let's do a substitution. Let's call v equal to x plus y, and let's see what happens. Hey, that's a good thing. That means that's something that we can solve for y, and that's important. Now, why that's important, you should know right now. Why that's important is because we need to do 2 things here. We're going to wrap up that composition as v. All our y's have to be there. But then we also have to change our dy dx, which means you're going to have to solve for y to do that. So we looked at it, said, doesn't look familiar to me. That has all of our y's in it. That is a composition. Let's call that v. Let's solve for y. We know that we're going to replace this with v, but we also have to replace dy dx. So let's find dy dx. So why we solve for y is so that we can do this right here. We know that we're going to have a chain rule implicitly on v. Minus 1 because the derivative of x with respect to x is 1. And now we're ready for our substitution. So we realize that this will be v. So x plus y gives us v. So we're going to have v. We're not going to have dy dx anymore. In fact, we found that right here. We're going to have dv dx minus 1 and then equals 1. So the substitutions can look confusing if you're not getting it. So I'm going slow right now just so it makes sense where these things are coming from, because this whole thing is going to change drastically. The only thing that's going to be here is 1. That's the only thing that's from the original differential equation. So right-hand side, we've got 1. Left-hand side, we're going to call this part v. We're going to call dy dx exactly what we found when we took the derivative of our substitution, dv dx minus 1. Also, you don't get to just assume this is v times just dv dx. The dy dx is this whole expression. You need parentheses there. So let's try to go on. We've made our substitutions. We know that all this stuff is dv dx's and v's and x's. There's no y's up there, and that's what we want. So we know that we're trying to get a separable equation. Let's try to make a separable equation out of this. Let's divide by v. At least that way we've got dv dx minus 1 with no v's over there. So remember, if we're trying to get separable equations to separate our variables, we need to first group everything together as a product or a quotient, and that -1 screws us up right now. And we can't just add it. That's why it was important for you to see the parentheses, that it's all multiplied together. So you either distribute that, probably not a good idea, well, you could do that, then you would add the v, or sorry, subtract the v, divide by v, that's fine too, you could easily do that. But here I chose to divide by v. I'm trying to get everything together as a product or a quotient. That right there is not a product or a quotient because I'm trying to get a separable equation. So let's add 1. That's still not a product or quotient. Let's find a common denominator. We know that 1 over v plus 1 is the same thing as 1 over v plus v over v. V over v is 1. Or we now have a quotient. That's what we're looking for when we try to separate our variables. We're looking for a d whatever dx equals some sort of product or quotient, because then we can just multiply or divide to group our v's, dv's in this case on one side, our x's, dx's with our constants on the other side. So we're going to multiply by the reciprocal here, or you can think divide by x plus 1, multiply by x, however you want to think about it. We need our v's on the left, we need our dx on the right. That looks real, well, it doesn't look great, but it looks like something we can do. So we have integral of v over v plus 1 dv, we have integral of x. That one's easy. This one is, well, we might have to think about that a little bit. It looks deceivable. It looks deceivingly easy. It's not necessarily that easy. We could try a substitution, but what are you going to do with that v? So if u equals v plus 1, we could do, there's a couple ways we can think about this. One way that you could do this, you could do u equals v plus 1, du equals dv, and you go, well, that doesn't help me at all. Right, but if you solve for v equals u minus 1, then you can create this. V is u minus 1, v plus 1 is just u, and it was still du. And then you can separate this into two fractions, u over u minus 1 over u. That's 1 minus 1 over u. That would be u minus ln u. And you can totally do that. That's one way to go. That's the substitution technique. I prefer doing that. So this is fine. If you like that, do it. Cool. I like this idea because I want to show you it's possible. I use it a lot if I can. So what we did is absolutely fine, but check this out. What if I just force this to be that separable fraction already? I mean, how do I separate that? I can't separate the v plus 1. Yeah, you're right, but watch what you could do. Could you just add... That might work. Could you just add 1? Well, no. Could you add 1 and subtract 1? Verify that that's still v on the numerator. Yeah, but now it's kind of interesting because I could choose to group this as v plus 1 over v plus 1 minus 1 over v plus 1. Is there really any difference in doing that besides a substitution? No, not really. It might save you a step because you have you don't have two substitutions, you got to go back from u. But this is going to look, and should look exactly the same as what I just erased from the board. V plus 1 over v plus 1 is 1. Minus 1 over v plus 1, that's nice. That's just like 1 minus 1 over u. Oh my gosh, u is even that v plus 1. It's the same thing. So either way you want to go with that, cool. I just want to show you this technique because it saves you a little bit of time and it's kind of interesting and we use it in other places. So integral of 1, well, that's v. minus integral of 1 over v plus 1. That's ln absolute value v plus 1 divided by the derivative of v plus 1, which would still be 1. So just ln absolute value v plus 1. Here we get v, here we get ln absolute value v plus 1 divided by the derivative of that. Cool. On the right hand side we get x plus c. We're looking pretty good so far. So let's see what else we can do. Man, would that be easy to solve for v? Well, if I start solving for v, I'd have to add an ln on both sides or subtract a v, and that's going to separate my v's. I can't factor out a v. This is not one that I'm going to want to solve explicitly. So this is about as good as we can make it without going crazy and without getting v's just everywhere. So right here, this would be an appropriate time to plug in our substitution again. So we substitute one time to get away from y's into v's, and now we're going to substitute another time to get away from v's back into y's. So since we can't solve this effectively or efficiently for v, we're going to plug in our v right now. So we used it one time to get away. Now we're going to say, hey, if that v was x plus y, now we can substitute that back. So we replaced x plus y with v. Now we're going to replace v with x plus y. So here we get x plus y minus ln absolute value x plus y plus 1. Don't forget about that plus 1. This v is x plus y plus 1 equals x plus c. There's only one more thing we can do. We have an x here, we have an x here, we can subtract x. So if we subtract x, we get y minus ln absolute value, same junk, equals c. That's about as good as we can get. We can't really solve for y that efficiently here, so we're going to leave it implicit. And that's a solution to our first order differential equations. I'm hoping that you're seeing this substitution technique. I'm hoping you're seeing it. It's a lot like homogeneous, where we just had a composition, but now that composition is not the same thing all the time. It can be wherever you have all of your y's wrapped up into something you can substitute and solve for y. That way you replace that composition and dy dx. Stick around for one more. We have a kind of a longer problem here that we'll go through. It's kind of fun. Has some different integration on it. Well, different things that we can do with integration on it. All right, let's wrap this up with another problem. Again, the first part of it, we're going to look at this as a composition. We're going to make a substitution. I'm doing this problem so you see another integration issue that we're going to have. So last example on the obvious substitutions, and hopefully by this time they're looking a little more obvious to you. Oh, okay, I see what you're talking about. I see a composition here. I see that you have a square root. I see that you have something that incorporates all of our y's in there that you could just wrap up as a v and take it out. And that's exactly what we're going to do. So when we take a look at this differential equation, yeah, does it look good? No, it doesn't look separable. X's and y's are both under the same function. That's the point of a composition. It doesn't look linear, same reason. Does it look like a homogeneous? Maybe, but maybe there's something nicer. Maybe there's something that we can say, you know what, all of those x's and y's, all of those y's in particular are wrapped up inside of a composition. Let's make a substitution and just get rid of it. Also, if we look at our composition, we can solve it for y. That's an important piece. So if you make that substitution, you also need to be able to get rid of that dy dx. Let's call that whole inside, that whole composition, v. We can solve it for y. Let's do it so we can find dy dx to substitute for the other side of our equation. Let's find dy dx. We always get a chain rule, so dv dx minus 1, derivative of 1 is 0. So now we're ready for our substitution. You should try it right now. You should see if you can take this, substitute the two appropriate pieces, and figure out what we have. So for us, we have the square root. We didn't substitute for that. It's the composition, the composed part, the inside part that we're actually substituting. So on the right-hand side, we're still going to have a square root. inside that square root, we no longer have x plus y plus 1. We wrapped all of that composition into v. On the left-hand side, we actually no longer have dy dx. We solved for y. We took a derivative. dy dx is this piece. Let's do that. Now, in your head, what I want to build there, I want to build that when you do these substitutions based on composition, that includes homogeneous, that includes substitutions that might seem obvious, and one other one. You're trying to get separable equations, which means this thing got to go. We're going to have to add 1 so that we can separate our variables. In trying to get that separable equation, those separable variables, we need to group everything on one side. That's important because, well, if you're trying to get a separable equation, you need stuff that's multiplied or divided. And this right here would become its own factor. You go, well, how's that a factor? You could think of that as multiplying by 1, but for a separable equation to work, you need to be able to get all of your stuff that's multiplied and divided. That way you multiply or divide, you get your variables on one side with v, your v on one side with v, x on the other side with x. With pluses and minuses, we can't do that. So if you're going to try to make a separable equation, you need, if there's any pluses or minuses, they have to be inside one factor. That right there is your one big factor. So we're going to divide both sides by the square root of v plus 1 dv, and then equals dx. That's pretty good. That's exactly what we want. We want to be able to group all of our v's as on one side dv as a product next to dv, and then we want, or a quotient next to dv, and we want products next to dx. That way we can go ahead and integrate both sides. On the right-hand side, that's nice. On the left-hand side, that's kind of nasty. So let's walk through it and think about what in the world we might want to do with that. Is it a basic integral? No, not really. Could I separate my fraction? I can't do that either because we have 2 terms on the denominator. Can I do a basic u sub? Not really, because we don't have anything to get rid of that square root of v. Is it, let's see, trig sub? No, the square root doesn't go the whole way across. There's no power 2 in it, that's a problem. Man, partial fractions? No, the square root. Maybe I could do like a double sub. And this is going to look a lot like the last example. So let's do a substitution. Let's see what we have and see if we can re-substitute for a factor of v that gets in there that we don't want. So let's try that. So if we have u equals square root of v plus 1, well, we need to find du. That's 1/2 v to the negative 1/2 dv. And let's solve this for dv. So we have 1 over 2 square root of v dv. And if we multiply both sides, we get 2 square root of v du equals dv. So you go, well, that doesn't look good. That's not what I have here. Yeah, that's true. That's not what I really want. I don't want a square root of v in there, but I'm going to have one. Maybe we can use this to get rid of that square root of v. So let's see what happens here. We have our integral. Here we got a 1. That's not a problem. On the denominator, we called all of this u, but then our dv. So we said square root of v plus 1, that's u, so we got that. But we solved for dv. So dv is not going to be dv anymore. It's going to be 2 square root of v du. I had a 1 here, but since I replaced the dv with 2 square root of v du, we can put that in place of our 1. 1 times 2 square root of v is 2 square root of v. Now, we always know in integrals that your variables have to match up with your integrating variable. So that square root of v's got to go. Well, that's why we use this substitution 2 different times. We say, well, u equals square root of v plus 1. Then square root of v equals u minus 1. Oh, well, if we take our 2 out, and we say the square root of v is u minus 1 over u, now that's something that we can separate into 2 different fractions, and this looks identical to the last example that we did. This is pretty nice. U over u is 1 minus 1 over u, that looks pretty good, du, and we can go ahead and we can integrate. One thing here, when you integrate and you get u minus ln absolute value of u, that 2 is so important. That 2 is really important for us. I know I'm omitting the right-hand side. It's just the integral of dx, so we're going to get x plus c. We all know that. But the 2 I want you to focus on. You cannot just forget the 2. You can't just put the 2 right there. It's going to screw everything up for you, all right? That 2 said you're going to multiply that 2 by whatever you got for your integral. It's going to distribute. So we know that this is u minus ln absolute value u. We know it came from a substitution. Let's put that back. So square root of v plus 1, looking pretty good, minus ln absolute value square root of v plus 1 equals, on the right-hand side, all of this was just equal to integral dx, and integral dx, and integral dx. So that means we're going to get x plus c sub 1. Some of you might be wondering why I do c sometimes and why I do c sub 1. I'm looking ahead and I'm thinking, am I going to have to modify that arbitrary constant? If I don't, I just put c. If I do, like either I divide or I add or subtract constants, I'm going to be changing that. So I'm looking ahead, seeing whether I'm going to change it or not. In this case, I'm going to. Now, man, that does not look easy to solve for v. So I'm going to do one thing. I'm going to distribute the 2 . And I want to show you something here. Some of you might be getting answers. You go, this looks, man, it's so close, but something's wrong. Why am I not getting the exact answer? Sometimes things like this happen. So this is fine, and this is fine, but that 2, that's a constant. And if you were to subtract that constant, that's a constant too. If you subtract a constant from a constant, you're still going to get a constant. And since it's an arbitrary constant, and we don't care what it is, a lot of times people will do this and say, that's a constant, let's subtract it. This constant over here, that's still a constant. Let's call it an arbitrary constant since it doesn't matter. Imagine this, say, well, this to the infinity, and the other person says, this to the infinity plus 1. You go, that plus 1 doesn't do anything. Exactly. If you don't care what constant this is, subtracting 2 is not going to make a difference. So we don't care what constant that is as long as it's constant. This happens quite a bit. So if you're getting answers that you have constants and they don't, probably they're adding or subtracting and grouping that as one arbitrary constant. So we'd have our 2, we'd have our square root of v minus 2 ln absolute value square root of v plus 1 equals x plus c. That is just nasty to solve for v. If it's even possible, it would be very difficult to do. I don't want to start dividing by 2's. That would be still a constant, but that'd get 1/2, so I'm not going to do that. I can't really solve for v's here. So the only thing that's left for us to do is use our substitution that gave us v's to get back our x's and y's. So, and sure enough, when we look at it, hey, v's inside a square root, just like we started with. And that's our composition. Let's just put x plus y plus 1. That's what v was defined as. And even though it's not explicitly solved for y, that still counts. That's fine. That's an implicit solution to our differential equation. Kind of nasty, but I'm hoping that you see what this obvious substitution technique can do. It's very similar to homogeneous in that you have a composition that you're calling v. In that composition, you have to be able to solve for y. In that composition, it has to include all of your instances of y. When you solve for y, you can substitute for not only composition, but also for the dy dx. That's great. So it'll all be in terms of v and x. Then we want a separable equation. So we group our variables on one side as factors or as fractions. We separate our v's, dv's on one side, x's, dx's on the other side. This constant doesn't count as a constant that you'd want to leave here on the x side because it's added. And that's not the constant we're talking about. When I said constant factors can be left there. Well, if we're talking about separable equations, you need factors, stuff that's multiplied where all pluses or minuses are in those parentheses. Then we go ahead and move that to the other side. After we get separable equations, hopefully it's an integral that doesn't have to be easy, but hopefully it's an integral we can do. And then if we can, we try to re-substitute for x's and y's and solve for y. If we can't, then we just re-substitute for x's and y's and we leave it. And that's about, let's see, that's about as good as we get. Unless I made some mistake, then we get this as an implicit solution for our differential equation. I hope it's making sense. I'll see you for the next video when we talk about Bernoulli equations.